All right, so today we are doing A/B testing. We're finally back to coding. Although it's A/B testing, I will be going through an A/B testing example in this notebook as well. But I did want to talk about power analysis. I think that is something that I guess through a slide deck, it's kind of fuzzy what that means. So I'm going to set up a scenario. This scenario does come from one of your labs, but I'm going to set up what that specific lab is doing and talking about, because that one is the one that I get questions every time I go through this. I always get questions on this part. So I'm going to talk through power analysis and what that looks like in setting up an experiment. So we're going to do that with code, and I'll show you all how easy it is to use the built-in statistical testing methods. And then we will talk about A/B testing. We'll do a quick example as well. And there's certain things I want to point out. Okay, so to start, we have our usual libraries, and let's start with power analysis. And so this scenario, which is a pretty common scenario when it comes to setting up your experiment, I will say setting up an experiment is less common for, I would say it's not something that data scientists do procedurally so much, but in analyzing just things related to your experiment, and you'll sort of see as we go through it what becomes important. Yeah, it's more useful for describing your experiment rather than actually doing the experiment itself. And I will say, if we're looking at what is the most common use case of applied statistics for data science, it is actually not so much this, because a lot of times data scientists are more like interpreting things. So it's actually more A/B testing, not power analysis. So just want to go through this just in case. But I think it's important for you all to know context in which this might come up. All right, so lastly, we talked about how these 4 factors, sample size, effect size, alpha, and beta, are all related. Remember, we had that graphic where you can adjust one and the other 3 change. And in this scenario that we're going to set up, we're going to talk about how this is actually used, how this information with these 4 factors is actually going to be used. So let's just set up the scenario. A researcher wants to study how daily protein supplementation in the elderly population will affect baseline liver fat. The study budget will allow enrollment of 24 patients. So here we already immediately have a constraint on the number of patients or the number of subjects or observations we can have. So half will be randomized to a placebo group and half to the protein supplement treatment group, and the trial will be carried out over 1 month. And it is desired to see whether the mean change in the percentage of liver fat from baseline to the end of the study will differ between the 2 groups in the study. So we have our first constraint, which is the number of patients that we can have. And so since we're going to compare the 2 groups, we have a control group and an experimental group. Each group is only going to have 12 subjects. So our sample size is actually only going to be 12. In this next part, we'll talk about some other constraints. So researcher needs to know what power will be obtained under this sample size restriction to identify a change in mean percent liver fat of 0.17. So here's our other constraint. The change that we're looking for, the effect size, not exactly effect size, but the effect or difference between the 2 groups, we want it to be 0.17. Based on past results, a common standard deviation of 0.21, and we'll use this 0.21 in a little bit, will be used for each treatment group in the power analysis. So in this experiment, we're constrained by our sample size that we talked about already, 12, effect size of 0.17 difference, and alpha, 0.05. And so therefore, with these constraints, we want to find our power. And another way of phrasing power is the proportion of simulations where the null hypothesis is rejected. All right, so let's just set up some of these numbers that we already have, and we'll talk about how we find power. So first, we have our sample size of 12. And then for our control group, we have a mean of 0 and a standard deviation of 0.21. So here, in this experiment, the way that they set it up, they have it such that for the control group, the liver fat doesn't change. So they're taking the mean as like, I guess, before and after treatment, what's the difference? 0. And standard deviation, as they said here, common standard deviation will be used for each treatment group, 0.21. And then for the experimental group, we're going to see a 0.17 difference and a standard deviation of 0.21 as well. Here, because this is before we even conduct the experiment, we want to find out what the power of this experiment that we want to conduct has. So we're going to simulate, we're going to do simulations. And so we're going to simulate 1,000 experiments just to see what proportion of those reject the null hypothesis. I think this will also come together when we look at this procedurally. So the way that we're going to do this, and this code is actually in your labs as well. I have added a couple comments to this, but first we're going to set a random seed. I forgot if we've talked about random seed yet or not, but because a lot of these processes are going to be randomized, for example, and we're using some of the random library. I'm going to talk about what this is in a little bit as well. But basically random seed makes it such that if we have random seed 10, if you were to download this notebook and clone this notebook and run it yourself, you'll get the exact same numbers. So that's just for reproducibility. The 10 is, it really just takes any integer. So most of the time, if you want to have a reproducible random experiment, you just decide on a number that you want to do. So it's 10, sometimes you see 1, 2, 3, a bunch of random, whatever number you. So first we're going to initialize an empty array to store results. So this empty array is going to actually be an array of 1,000 zeros or NaN values to start. The reason for this, we'll see why in a little bit, but basically what we're going to do is this empty array is going to start with NaN values, and we're going to replace these NaN values one by one with the outcome of our simulations, of each simulation. So therefore, this empty array matches the dimensions of the number of simulations. So it's just going to be another, it's just going to be an array of 1,000 NaN values to start. So what's going to happen here for S, I guess for simulation, in range nsim, and range nsim really just means number from 0 to 999, so 1,000 numbers in total. We're going to repeat this experiment with random outcomes of our control and experiment group. So what we're doing here is we're actually, because we have yet to conduct this experiment in real life, we're just going to simulate these experiments. So first, we are doing our control group. We're going to just create a random control group, and np.random.normal basically samples data points from a normal distribution, matching whatever mean and standard deviation you want. So basically, with a mean and standard deviation of 0, 0.21, and then sample size 12. So it's just going to sample 12 data points from a normal distribution centered at 0 with a standard deviation of 0.21. It's just going to take 12 random points from that distribution. So these are just 12 random points from that distribution, and it's supposed to mimic what your results will probably be like if you were to conduct this experiment. So for each simulation, they're going to pick a different 12 data points from that distribution. They're also going to do the same thing for the experimental group. The main difference here is instead of the control mean, you're going to be using the experimental mean. So instead of the values being centered at 0 for the control, the values will be centered at 0.17. 0.17? Yeah, 0.17 in the experimental group. So 1,000 times, you're just going to grab 12 random, I guess, values from these two different distributions, and then conduct t-tests to see whether they are statistically significantly different. So for each simulation, we're going to compare these two groups. And this is the two-sample t-test code in Python, where you literally just do t-test individual. I think IND stands for, I actually don't remember what IND stands for, but you just feed it in your control array and your experimental array, and then it gives you two things, t-test returns two things, your t-statistic as well as your p-value. So for our purposes, we just need to compare the p-value to alpha. So what we're going to do is we're going to store our p-value. So therefore, this S here basically goes back to our empty array. Remember, we had like 1,000 NaN values. So it's just going to update each NaN value with the p-value. And index 1 is because t-test here, this output is a tuple containing t-statistic p-value. We just need to save the p-value. So let me just run these cells real quick. All right, so when I run these cells and take a look at these p-values, we have, this is basically an array of 1,000 p-values. And you can see that they kind of have a varying range. For example, this one seems to be like 0.2. This one is 0.002. This one is even smaller, but it really depends on how this random sampling was done. So these p-values are all different because each time the simulation is run, there are 12 different control points and 12 different experimental points. So this is what a simulation is all about. And you get your 1,000 different p-values. Now, the power of the test is the number of times that you correctly reject, sorry, is 1 minus, yeah, it's the number of times you correctly reject the null hypothesis. Yeah. So therefore, we're just going to look for how many times the p-value is smaller than 0.05. So here, we're going to see how many times the p-value is smaller than 0.05, and then divide it by 1,000, and then we will have the power, which is 0.495. This is just saying that out of 1,000 experiments, 495 times we correctly rejected the null hypothesis. So power is at this point 0.495. Any questions about this process so far?
The p-value here, what if it's like 0.95 or above? I guess my question is this p-value from the left tail or the right tail or both? Not quite sure.
Okay, I think by default, that's a good clarification. I believe this hypothesis is a two-tailed test. Yeah, this hypothesis is a two-tailed test. And then this, by default, I believe, actually, let me look it up. Stats, t-test. I think by default, it is a two-tailed test. Just look. Okay, so let's see. I think default is two-sided, yeah. So by default, it's a two-sided test. So your p-value will automatically update to be two-sided. And gotcha. Yeah. And this one, they will also multiply your p-value by multiply or divide. I'm confusing myself, but basically it will account for the fact that it is two-sided.
Got it. Thank you.
You're welcome. Anything else?
Just oh, go Mo.
No, it's all right. Go ahead.
Go ahead. It's fine.
No, just a real quick question. The random seed, where is like in the where is it?
That's a good point. Yeah. So this random seed, it works kind of interestingly. Like if you set a random seed at the start of a notebook, it actually uses the random seed throughout the rest of the notebook. So you really just have to like run that line anywhere and the random seed will be set.
But where is it in the sort of the output? That's
okay. So basically what this means is, okay, let's take a look at this first one, this 2.35, 3.83. If I were to change this random seed to like a different number, like 1, 2, 3, and if I run it, the numbers will change. The whole idea of this random seed is if you were to take this, okay, let's say we didn't have a random seed. If we didn't have a random seed, every time I run it, it'll be different. See 1, 1, 1, and then 4, 8, 4, and then 2.85. Every time I run it, it'll be different. This is really just so that your values will match like maybe the solutions, or if you're like sharing a notebook and you don't want your values to keep changing, you will just set a random seed. Usually, actually, it is set like at the very top. This, because I kind of I think I copied it from the solutions. But so if we go back to our random seed of 0.1 of 10 is what it was before, these numbers will be the same. And the reason why where random seed actually does come into play is anytime like a random thing is being used. So anytime like the random library or any I guess any method that uses some form of randomness, as long as you set a seed, it will do the same random every time.
I got you. So as when you're running any type of random test,
Yeah.
that's when it's in effect, basically.
Yes, exactly. So as an example, real quick, we can like take a look at this. Let's do maybe like, okay, this as an example. If I run this, let me just collapse this for now. Okay. So this is just grabbing like 12 random numbers with mean of 0, standard deviation 0.21, and sample size 12. So every time I run this, it will remain the same number. And then this, you can sort of think of it as like it's setting a notebook random, like setting a notebook consistent random. And then if I turn it to like 12, it changes, and every time it's a number. So if you were to run this exact code with a random seed of 12, you will get these exact numbers.
Oh. So the number in the random seed, if it's, I'm trying to understand like what's a proper number to use.
It doesn't matter what
Okay.
number it is. You can, I would say like, let's say for this upcoming project, if you want to like share your project with somebody else and you don't want the numbers to change for this coming project, you can just pick whatever number you want. And then if you send it to someone else and you want them to run the notebook, you'll get the exact same numbers. Yeah, the number itself doesn't matter. It just gives you a different set of constant randoms.
Okay, I got you. All right, thank you.
You're welcome. Amir, you had a question as well?
Yes, just in terms of like having the control experiment, the control and the experimental groups, would it be proper? Like I understand like for the example, like while you're doing it, but like in like like in the actual analysis, just because you don't have like either you don't have any like representation of the two groups, like would this even like would it be proper to use two randomly sampled groups other than just for the lecture today?
So yes, when you're doing a power analysis of an experiment that you haven't conducted yet, yes, you actually pretty much do, you do
Okay.
have to
All right.
randomly sample. And
Okay.
actually, if you remember, we set this mean to be 0.17, which is the actual difference that they want to detect. So therefore, sampling from this, you should actually, the idea is you do want to reject your null hypothesis every time.
Okay. All right. Okay.
Yeah. Yeah, it's a little bit abstract because this is like, we've been talking about conducting the statistical test, but this is sort of like prior to conducting an experiment, you can figure out the power of your test.
Okay.
Yeah. Okay. Sweet. So with this experiment, with these constraints of sample size 12, effect size 0.17, alpha 0.05, the power of the test is 0.495, which to say is about half the time you're going to incorrectly not reject the null hypothesis. And so you're going to incorrectly say that is it a drug? You're going to incorrectly say about half the time that this protein supplement doesn't affect liver fat when it actually should. So what can we do? Sometimes it depends whether you want to like adjust something. Usually you don't touch alpha because alpha is something that you should not adjust after figuring out your power because that's kind of like cheating. let's say you want to achieve a power of 0.8. Often in behavioral research, 0.8 is usually the sufficient level of power. That's just experimentally, and I guess an agreed upon number. I want to show you all this code real quick because this is the quick way to solve for any parameter. So this it comes from the library stats models, and it's solve power. So basically, it solves for any one parameter of the power of a 2-sample t-test. So you need to give it either one of effects, either 3 out of 4 of effect size, number of observations, alpha, power, and then ratio, I forget. Oh, yeah. If you have a different number of samples per group, then you give it a ratio. And then you can also give it whether it is a one-tailed test, and then you can actually say whether larger or smaller. But anyways, quick implementation of this. If the correct definition of effect size is actually the actual difference divided by standard deviations, which is why I'm taking 0.17 divided by 0.21, alpha 0.05, power of 0.8. It gives us because what we're missing right now is the number of observations. So they're saying to achieve a power of 0.8 with effect size remaining the same and with alpha remaining the same, if we want to get a power of 0.8, we need to have a sample size of at least 25. You always have to round up. So you always have to, you want to get a sample size of 0.24. Let's say, if we want to go back and look at this one, if we did, I always forget how you spell the number of observations because it's, oops, is this one? No, it's here. Number of observations is knobs 1. Okay, so we did knobs 1 equal to 12. This will give us 0.4746, which because this is 1,000 simulations, I think if you run this more and more, it'll actually get closer. It will get closer and closer to 0.474, but roughly the same, about the same number. So if we were to run this like an infinite number of times, the ratio should look more like 0.474. But just to show you that this solve power method, super powerful. But anyways, back to what we had before. Power of 0.8, it shows us that if we want to have a sufficient enough power, we should have 25 subjects per control and experiment group in order to maintain that we will correctly reject the null hypothesis 0.8 of the times, 0.8 of the amount of times at least. Another way to do this is iteratively. Here you can see we have a target power. We start with a sample size of 12, and what we're going to do in this iterative approach is keep increasing our sample size one by one until we reach our desired power. And then we're going to keep track of a couple things. How many times a null is rejected and the number of simulations we're going to keep at 10,000. And here we have a random seed again, just in case. So what we're going to do is while our null rejected, which is our power, is less than our target, we're just going to keep repeating pretty much the same thing that we did before. This looks confusing, but basically what we're doing is we are creating an array of that number of arrays so that it can save all of those p-values and all of those elements. So what we're doing here is pretty much the same thing. And then what we're going to do is calculate the power and then increment the sample size by 1. And then once your power hits the target, it's going to stop. So what we're going to see is when I run this all ran pretty quickly. At 12, we had a calculated power of 4.75. And as you increase the number of samples, power slowly increases. And then at 25, that's when we achieve enough power. I will say this code is pretty complicated. You probably never have to do this because you can pretty much just always do solve power and get it straight away. But just if you wanted to check out the Python code to do it iteratively from scratch manually, this is it. But I will also say that this is not need to familiarize yourself too much with this process. Okay, and then if you just want to see graphically what that looks like, power is just going to increase with sample size. Let's say we set our target to be 0.9. This will keep going until 34. And you can see that, again, power just gets closer and closer to 1. All right. Questions about this power analysis? I think this is the context in which you will be using like power of the test the most, if at all. So yeah, any questions or anything to clarify with this process? Typically
So-
you are, oh, go ahead.
Oh no, I was just gonna ask. So basically, the point is, we want to find, at least for this particular experiment, that we want at least a sample size of 25 using all this information. Okay.
Correct. Yeah. So typically you are going to be constrained by something. Typically alpha, you're not going to change your alpha. If anything, you make your test even stricter and set your alpha to be lower, like 0.01. And effect size, usually before you even begin an experiment, you're like, okay, if you want to come up with a drug, for example, you would usually be like, okay, this drug, I want to make sure that this drug can at least lower your mean percent liver fat by 0.17. So usually that's the number that you test for, that you constrain as your effect size. So then therefore, pretty much the only thing that you can vary is sample size, and that will affect your power. But of course, sometimes like really dependent on the situation of your statistical test. If, you know, in this case, there's like what I think here they said that because of like budget constraints, yeah, the budget will only allow enrollment of 24 patients. You can really just check the power and just keep that in mind as you're conducting your experiment. Just to keep in mind that like half of the hypotheses, of the null hypotheses that you reject, that you do not reject might be, what's the double negatives are confusing, but you might incorrectly not reject some null hypotheses. Yeah, that's what it is. So yeah, that's really just overall the context in which you would use power the most is this. Either to check for the power of the test straight up, which you can use with that one line over here. Oops, not this one, over here, this one line. Or the other way around to figure out the minimum number of observations you will need to achieve a certain level of power if you are able to vary that number. And again, this is all before you even actually conduct the test, which is an important thing to remember. All right, if there are no questions, let's move on to A/B testing. So A/B testing, I will say, is probably the most common application of statistics in the data science realm. I have actually seen a few students get like take-home interviews where they're asked to conduct an A/B test on some company's data. So I would say this is kind of important to know. So in this scenario, which is actually from one of your labs, I forget what the exact scenario setup is, but basically there's a change made to a website, and this change is only given to some users and not all users. And they want to see whether this change to the website has led to more click-throughs or has a higher click-through rate based on whatever change it is. You want to achieve more clicks or different clicks. So let's take a look at this data set. Here you can see that there's timestamp values, different IDs, whether the ID belongs to a control or an experiment group, and then the action, whether it is a view or a click. So this representation of data is pretty common just because every time there is some action taken, a data point is created. And so in this data set, you might actually come across, like you will probably come across multiple of the same IDs. So let's say we do, let's just take a look at more to see if we can find any clicks. I guess this won't show me all of them. Let's see here, whether there's any clicks. Okay. So here, for example, we have ID number 349,125, which belongs in the experiment group, viewed and then clicked like 1 minute after. Let's see this example as well. experiment group as well, viewed and clicked within a minute of each other. So we just want to see the click-through rate between control group and experiment group. So doing a very, very quick EDA, number of viewers, 6,000, number of clickers, 1,800, number of viewers that didn't click, 4,468, number of clickers who didn't view, 0, which makes sense because if you didn't view it, you probably cannot click it. So first what we're going to do is we're going to separate these two data sets into, this is just the control group, just the experiment group. So then we can take a look and to see that, for example, the experiment is only the experiment group and the control is just the control. This next section is really just going to make it a little bit easier to calculate proportions. This is only one way to do it. There are other ways to do this, but this is what the labs have. What we're going to do is we're going to add just a count column, and this will help us to sum up the click-through rates. So let's just take a look at this real quick. I'm not going to explain this code too much, but let me show you all. What they did is a pivot table just to show for the control and experiment group, the data frames are going to look like this. The IDs and the index is ID. So you've basically, for those IDs that appeared in multiple rows in this data set, they're just going to be combined into one row. And then they've turned the click and view into dummy variables, into like categorical variables on whether they clicked or not. For the most part, the views are pretty much all going to be ones, and the click is going to be 0 and 1, dependent on whether they clicked or did not click. And this will just help us more easily calculate our proportions. So sample size in our control group, there was 3,332, experiment group just under 3,000. And the total number of clicks for the control group was 930, experiment 928. So you can sort of see here that the click rate is pretty close, but we want to see whether it's statistically close or not. So the control group's click-through rate is about 28. The experiment group's click-through rate is about 31. So what we're going to see is, what we want to find out is whether this difference in about 3, this 0.03 difference in click-through rate, is it statistically significantly different to say whether that change on the web page has led to different number of clicks. Okay, so these are formulas from the labs that feel free to write if you want. I will also show you the actual way to do it, but these are formulas that you can set up in your labs. You basically calculate your t-statistic, calculate your degrees of freedom, and then you actually conduct the t-test by calling on the t-statistic and the degrees of freedom functions here. And when you run that, you get a p-value of 0.008. And this is for a two-sided test. I forgot what the solutions say, but this is as a two-sided test. I know it does say more or less, but let's just go with two-sided for now. So based on this p-value is less than 0.05. So there is only a 0.008 chance that this difference in click-through rate is completely by random. So therefore, just based on this one line, one number output, we actually do see that 0.03 difference in click-through rate is statistically significant. Even though it's very small, it probably is because of the larger sample sizes that lead to a more significant difference. Alternatively, if you don't want to write these functions, and you really should not, you can use SciPy, same code that we did before. This is really just comparing the click columns of control and experiment, just to show you all what that looks like. Control.click is basically a bunch of IDs and ones and zeros, and then same for experiment. And the idea here is, experiment. There you go. The idea here is that experiment should have more ones proportionally versus control. And just by doing that same thing, you get the same p-value, roughly the same p-value. Here you basically have some rounding error, but you have pretty much the same p-value here to reject the null hypothesis. And just in case you want to check that, you have your t-statistic of negative 2.62. So I would say if you were ever given a some sort of like task or interview where you had to conduct a t-test. Important part is mainly in setting up the data frame, but also just know that conducting the actual t-test is the easy part. You really just have to, sort out your data such that it comes in this format, and then you can just run your 2 sample t-tests, whether it's one-sided or two-sided. As you saw earlier, this does support one-sided and two-sided, so you can do that. Depending on what the question is asking for, you can do this. And actually, if I show you all that, like, this does actually change the p-value. So if I do alternate equal to, I think, greater or less, alternate equals to greater, oops, alternatives, yeah, alternative equals to greater, the p-value is actually almost 1, so it's definitely not greater. And then we can take a look at less, there's 0.0044. I think it's because if you flip, I think it really depends on which order you give the arrays, and I forget which one is which at this moment. But yeah, to do an A/B test is really just a 2 sample t-test. So yeah, any questions about this?
I just want to ask, so the 0.03 as compared to the 0.008, what are you comparing? What's the comparison?
Okay, so what we're seeing is this difference between the click rate of the control group and the experiment group. The difference here is 0.03. Right, and we want to see if that difference of 0.03 is statistically significant or not. Like whether they are significantly actually different, or is it just like by chance, the people in the experiment group just so happened to click more, just like randomly decided, like it just so happened to be that the people in the experiment group were just, more, have like a higher propensity to just click things. And so we're basically comparing these 2 ratios, and one metric that we can use to confirm, or one metric that we can use to measure how statistically significant a difference is the p-value. And basically, the smaller the p-value, the more significant the difference is.
Oh, okay.
Yeah, that's another way to phrase it.
Right.
Yeah, so in this case, it should not be, if we go with it as a two-tailed test, we have a 0.008. So that's just saying that there's only a 0.008 chance that this difference of 0.03 that we observed happened by random chance, which is to say that there's a pretty solid chance that there is a significant difference in the click-through rates of these 2 groups.
Oh, okay, so basically, because it's a low p-value, it's a greater chance that it was not
true. Oh yeah, go ahead.
No,
I think you're about to say the right thing.
I hope so. But basically, because it's a smaller p-value, it's a greater chance that there was a difference.
Yeah, exactly. There's a greater chance that this observed difference is due to the change on the website. The change of the website did actually lead to a significant difference in the click-through rate.
Oh, okay. All right. Thank you.
Yeah, you're welcome. Any other questions? Cool. I will say that after this topic, we're not really going to come back to A/B testing, because A/B testing doesn't really include much machine learning at all. And starting next week, it's all going to be like machine learning from then on. So this is something that's good to refer back to, especially like when it's time for like interviews and stuff, just to let y'all know.
Another question, sorry for another question.
Yeah.
For A/B testing, With this, I know like you have your p-value, right?
Mhm.
Like would just like using an A/B test be significant in like determining if a value ended up, even though a p-value does do that, but just to verify that like the values that you're using are significant towards like, let's say you were to do like machine learning, let's say you have like a multiple like linear regression, and like you wanted to determine like, okay, like which 5 values are you going to use? Could you use like this like preemptively before you
Yeah,
go this?
I would say, mm, we're gonna actually see t-tests being done in the context of linear regression.
Okay, that's different. Okay, all right.
Yeah,
I'm thinking of
yeah.
myself. Sorry.
I would say like if you want to do a t-test preemptively as you're leading into your regression, just to confirm that, hey, maybe this will be a good thing to include. And I will get into this next week as well, but you can actually do that. Like if you think that like, let's say, and our project, the provided data set is predicting housing prices. And so let's just say one of the features that you're thinking of including in your analysis that you think can affect housing prices is, okay, I know that one of the features that you get is like, or one of the columns you get is whether the house is a waterfront house or not. And
Mhm.
so if you really think that a house being on the waterfront should really have an impact on the price, you can do a t-test or pretty much an A/B test on like, or a 2-sample t-test, which is pretty much the same thing, between houses that don't have a waterfront and houses that do. Take all their prices and conduct a 2-sample t-test, and then you can see whether there's a significant difference in the prices of houses, depending on whether they have a waterfront or not. That's actually a good preemptive strategy to
Okay,
decide on
that's what
whether to
I,
keep
that's
something
all
like
right.
that.
Okay, yeah, that's what I was.
Mhm.
Yeah. Okay. Cool.
Awesome. Yeah. Same thing goes for like if you have like, let's say you have a category of like, let's see, what's an example? Let's say you have different grades of houses. I don't know if houses, yeah, there's a grade column. I forget what that means, but let's say you have like grade, like houses grade like ABC, for example. If you remember last time we talked about conducting ANOVA tests, which is basically the same thing as conducting multiple t-tests for everything, you can actually conduct an ANOVA test. And if you see that there's a significant difference between the mean prices between each grade group, then it is usually a clear sign that yes, you can use that, or it is a motivating factor for including that feature in your model. And if currently all this modeling speak is going like over your heads right now, all good. We're going to talk about that next week.
I had another question. Just to go back to the p-value, if it was, what would be, would the number be more than 0.03 that would say that it wouldn't be a difference in this scenario? Or what would be the number, what would be the p-value that would say like this is, the change didn't make a difference?
Right.
Would it be
Okay.
more than 0.03?
More than 0.05, because this is something that we compare to our alpha.
Oh, okay.
Yeah.
All
And
right.
then, yeah. So basically compare p-value to your set alpha. Mhm.
Okay. All right. Thank you.
You're welcome. Cool. Anything else? All right, if there's nothing else, tomorrow's session, we're going to go over Bayesian statistics, which I'm actually going to save a good chunk of it for phase 3, because I feel like it connects directly to one of the machine learning models that we're going to talk about in phase 3. So tomorrow's session, I'm actually going to focus more on like solving a probability problem using Bayes' theorem. If you remember that concept questions document, basically this question, which includes some of the things that I talked about back in like topic 11, like law of total probability and Bayes' theorem. A question like this is something that we're going to walk through basically this question tomorrow. And on top of that, I'm going to talk about maximum likelihood estimation, which is an extremely abstract concept, but it is good to know as we're leading into machine learning. And it kind of connects with the central limit theorem that we talked about before. Maximum likelihood estimation is I would say out of statistics, one of the harder things to understand. But if you do understand it, it gives you a good intuition for machine learning modeling. But if you don't, honestly, you can get by without fully understanding that, because it is a pretty tough concept to grasp. So just a heads up on that, that's coming tomorrow. So after tomorrow, you actually should be able to answer all of these questions. And I will say that if you feel comfortable, or if you're able to, like, you know, maybe you have to look it up, which is fine. But if you like can take all of these questions and write out your own answers in your own words to these questions, that would be perfect interview prep for next time. Or like, yeah, it'll prepare you for when you're about to prepare next time, so that you'll have your answers there, because these are the questions that do come up most often. All right, any final questions? Going once, going twice. All right, if there's nothing else, I will see you all tomorrow at this time. And as usual, you all know, any questions you have, just Slack me and let me know. All right, have a good rest of your evening, guys.
Thank you, everyone.
Bye.
Thank you,
Bye, guys.
Good night.